The basse-chaine bridge was one of the finest suspension bridges in France. Its engineers had calculated its load capacity to the ton. 226 soldiers. They weighed, in total, roughly 60 tons. The bridge could carry 10 times that. That was not a guess, that was the mathematics. On the morning of April 16, 1850, a regiment of French infantry marched onto it, in step. The bridge began to shake. Within 90 seconds, it was at the bottom of the main river. 226 men drowned. The weight didn't kill them. The rhythm did. And the reason is one of the most important lessons in the history of structural engineering, a lesson that had never been learned before this morning because no structure had ever paid this kind of price to teach it. The basse-chaine suspension bridge had crossed the main river at Angers in western France since 1839. 11 years old. It had carried thousands of carts, pedestrians, and livestock. It had never failed. It had no reason to fail. The engineers who designed it understood suspension bridges as well as anyone in the world at that moment. A suspension bridge works by hanging its deck from cables, in this case, iron chains, that arc over tall stone towers and anchor into solid ground on each side. The chains carry the entire load. The deck is simply a platform suspended beneath them. It is a system that has been trusted to carry enormous weight across vast spans. The load calculations were sound. You sum the deck weight, the chains, the maximum plausible number of people. You apply a safety factor. You design the chains accordingly. The basse-chaine's chains were designed to carry several hundred tons before failure. 226 soldiers in full military kit weighed perhaps 60 tons. The chain's safety margin was enormous. No engineer alive would have hesitated to call this bridge safe. The assumption was static. The engineers were calculating force, how much weight. They were not yet calculating frequency, how often, how rhythmically, how repeatedly. That distinction was not yet in the engineering textbooks. It was about to write itself there. The morning of April 16th was hostile. A storm had been pushing in from the west since the previous night. Heavy rain, high wind. The sky was the color of iron. The 3rd Regiment of the line had orders to march from Angers to a military exercise. The basse-chaine bridge was the direct crossing. The officers gave the order: cross. 226 men filed onto the bridge deck in close formation, in step, left, right, a steady cadence of approximately 100 paces per minute, a perfectly normal military march. An officer near the front felt the bridge move beneath his feet, a sway, lateral, rhythmic. Suspension bridges do flex. They are designed to. He noted it. He did not order a change of pace. The bridge was swaying in time with the march. Nobody on that bridge yet understood what that sentence meant. Every physical structure has a natural frequency, the rate at which it prefers to oscillate, its own internal rhythm, set by its mass and its stiffness. Push it at a different rate, and it absorbs the disturbance and returns to rest. Push it at its own natural rate, and something different happens entirely. It adds. Every push timed to the previous swing makes the next swing wider. The energy doesn't cancel, it accumulates. Each cycle, the amplitude grows. This is called resonance. It does not require a large force. It requires the right frequency, repeated. The basse-chaine bridge had a natural oscillation frequency of approximately 1 to 1.3 cycles per second. The marching pace of the regiment, 100 steps per minute, was also approximately 1 to 1.3 cycles per second. Left foot, right foot, the exact rhythm the bridge wanted to swing at. Each step fed the oscillation. The deck began to swing wider. The cables pulled taut and then slackened, taut, slack, in a rhythm that was growing. Not fast, not all at once, one cycle at a time. The chains were 11 years old. Iron chain links immersed in a riverside environment develop surface pits, micro-damage from corrosion that no visual inspection at the time could quantify. Those pits are points of concentrated stress. When metal is bent back and forth repeatedly, millions of times if you count every oscillation across 11 years of service, cracks nucleate at those points of concentrated stress. They are microscopic at first, invisible to the eye. They grow with every cycle. This process is called metal fatigue. The deck was now moving violently enough that men were losing their footing. Some grabbed the side cables. An officer shouted the order to break step. Whether the words carried over the storm or came simply too late, they did not reach the regiment in time. One link failed, a fatigue crack that had been propagating invisibly through thousands of oscillation cycles, each cycle adding a fraction of a millimeter of growth, reached the far boundary of the iron. The link separated. In a chain suspension system, one link failing means the entire load redistributes instantly across its neighbors. Those neighbors were already fatigued. They failed in cascade. The deck lurched sideways, then the cables parted completely. Then the deck dropped. 226 men entered the main river. Cold water, a fast current, full military uniforms and equipment. 226 did not come out. The investigation commission spent weeks on the wreckage. They recovered chain links from the river bottom. The fracture surfaces were read by trained eyes, beach marks, the fingerprint of fatigue failure, showing that cracks had propagated across many thousands of cycles before final fracture. This was not overload. The soldiers had never come close to the bridge's static load limit. This was resonance, a tiny, perfectly timed force repeated at exactly the right frequency, building energy that the chains could not release. Physics taking from an assumption everything the assumption had failed to account for. The basse-chaine bridge was eventually rebuilt, but what happened here changed something much larger than one bridge over one French river. Every army in the world now carries a standing order: break step on bridges. The moment a formation sets foot on any bridge, the march becomes deliberately ragged. Officers call it soldiers comply, purposefully unsynchronized. The specific reason this order exists in every military field manual on Earth is what happened here on April 16, 1850. And the engineering lessons went further. Modern suspension bridges and footbridges are now designed with their resonant frequency calculated before the first stone is set. The goal is to ensure the bridge's natural frequency cannot match any load frequency it is likely to encounter: pedestrians, vehicles, wind. When geometry alone is not enough, engineers add tuned mass dampers. A tuned mass damper is a large weight mounted on springs inside the structure, calibrated to move in the opposite direction to any resonant oscillation, actively canceling the swing before it can build. In 2000, the Millennium Bridge in London opened and immediately began to wobble. Pedestrians, without knowing it, synchronized their steps to the bridge's lateral sway. The same mechanism, 150 years later. Dampers were installed. The problem was resolved. The physics did not change across those 150 years. Only the engineering knowledge changed. The knowledge that Angers paid for. Resonance doesn't need a big force. It needs the right frequency, applied at the right moment in the right rhythm, and it will take apart any structure that assumes the world is static. The next time you see a column of soldiers break step before a bridge, staggering deliberately, awkwardly, they are not following an old superstition. They are following a lesson written in iron and cold water in 1850 by 226 men who had no idea they were about to teach it.